Okay, I will try to make a video. I hope it will work. Here it's a little bit noisy, but okay, whatever I have. It's this presentation about optical instruments. You will make also a quiz about the optical instruments, and then it is very big topic actually, and we are supposed to take 3 hours to investigate this topic. Okay, let's go. And we will talk actually not about all optical instruments, but mostly about microscope, telescope, and some gratings to measure spectrum of the some substances, and about eye, how eye works, and camera, for example, also. So maybe the simplest optical instrument, what we know, it is camera, CCD camera, or maybe film camera. So how it works? It has lenses. It has one, or actually mostly in more expensive cameras, it has objective lenses, which are compounded, which have not one lens, but maybe 2, 3, and more. And they have all this camera is in box, and it has CCD matrix, or it has a film. Film, it is like to produce picture on emulsion, on photo emulsion. So what we have with this camera? We have image, real image, because it is projected to the screen, and it is inverted, and it is reduced smaller, size is smaller than object, of course. Okay. How it operates? You have to focus camera, so you're moving lens here, and here you are changing position of the lens to get really easy focused, sharply focused image to the CCD matrix or to the film. And also you have a shutter. Shutter is it is mostly for film camera, but also for CCD camera it is used. It is open only for selected time intervals. And time interval, this you decide manually or it is automatically. Next, what you have aperture. Aperture, it is you are changing the diameter to control intensity of light which is coming to the film or to CCD matrix. But of course, small cameras, not expensive cameras, they have small diameter aperture. Well, okay, and the larger the size of this aperture, the more light is coming in. So the light intensity is proportional to diameter of the aperture squared. So it is proportional to the area of the lens. And therefore, the brightness of the image, which is formed on the film or CCD matrix, is about proportional to diameter of the aperture of the lens, and divided and oppositely proportional to focus, d divided f squared. Okay, then again, this is more expensive objective lens for film or digital camera. So it has focal lens. It has also this aperture, which is normally done in ratio of focal length divided d divided size of the aperture. Some not expensive cameras, they have small diameter, small aperture, and they even some of this camera, like camera in your telephone, they even have fixed position of the lens. So the focal length is fixed, aperture size is fixed, and therefore only central part of the lens is working, and because it's only a central part is working, not so much light intensity which is of light is which is coming to CCD matrix or to the film is small, and then it cannot work in low light conditions. You need good illumination for this camera to work. And also resolution, so quality of the picture is sometimes not very high. Okay, let's consider the design and how our eye is made. I mean, what parts of the eye. So we have to understand, this is kind of biology, but we better understand it, better consider eye as an optical instrument. So what we have, essential parts of the eye. We have this cornea. Cornea is a kind of protecting layer at the front of the eye, which is so light is passing through this transparent structure, and you have some liquid behind this cornea, and then you have what you have apertura, which is named pupil. You have here pupil. You have or here it is visible here a pupil, and pupil is nothing more but variable apertura, so it can get larger or smaller. So iris pronounced, is getting smaller if an illumination is high, and in dark environment it is getting larger to collect more light, more intensity of the light. Then you have also this optical nerve, and you have retina. Retina, this is the inner surface of the eye with nerves, with optical nerves and sensors to the light. Okay, let's look about check this slide about iris. Iris is colored normally. Sometimes it is dark, sometimes it is more green and gray, or in some cases blue. So iris regulates amount of light that is entering the eye. Okay, it is automatically our eye is working so that the iris can be smaller in bright and in high light conditions, or it can be larger in low light conditions. And F number of the eye and F number of the Y you remember from camera, it is ratio of focal length to diameter. This ratio, or so-called F number, is about 2.8, and for very small iris it is 16, maximum 16. Okay, so you see again this ratio, focal length divided the diameter or apertura or the size of the iris. Okay, then maximum is 2.8 and minimum is 16. Okay, I mean 16 is the conditions when the iris is very small. Okay. The aperture is very small in bright and in high light environment, and then F number will be large, okay, up to 16 in low light conditions. Then we have this cornea system, and cornea system, cornea is, okay, we go here, and we see that cornea here, this is a lens type. It is working as a lens, but we have also another lens. We have cornea and another lens inside. So this lens system focusing light into the back surface of the eye, and this back surface of the light called retina. Retina, this retina, okay. Retina and or retina. Sorry, it's my pronunciation probably not perfect. Retina contains receptors of two types, rods and cones. And then these are actually sensors, and they are sending impulses via optical nerve to the brain. Okay, structure of the these cylinders and rods and cones. This is the rod. This is a cone. Rods and cones, they adjust the sensitivity to light condition, and adjustment takes about 15 minutes, and then it is shifted from high light conditions to the low light conditions. And but in low light conditions we cannot distinguish colors very good enough, so we see not the image will be in not so colorful. So accommodation. What is accommodation? What first we have accommodation by changing the shape of the crystalline lens. So we have this lens which can be stretched by muscles, can be stretched and therefore can be thinner in the middle, or thicker. Okay, it is elastic. And we have this muscle which is stretching this lens. Okay, so let's go next. So the eye can focus on a distant object if the muscle is relaxed. Relaxed means that the lens is getting flattened and increase focal length. For an object at infinity, f is equal to about 1.7 centimeters. This is the distance between lens and retina. Retina and lens, 1.7 centimeters. It is about the size of the eye. Also, eye can get focused on near objects. Then muscles are pressing on the lens, and lens is getting thicker in the middle. It gets thicker in the middle, and then the lens, focal length of this decreasing. So this allows to eye to be focused on near objects. Okay, then again we are talking about near point. Near point is the closest distance for which the eye can accommodate. It is accepted that it is 25 centimeters, but it can be smaller. Of course, it can be smaller, and if it depends on elasticity of the lens, and it depends on the shape of the ball, of the eyeball, also. But in average, it is 25 centimeters. Problem with this distance that older people. In older people, this lens is losing elasticity, and therefore people cannot get focused the eye on close objects. This is a problem. And again, it is little bit aside of the optical instrument about biology. Why it is losing elasticity? Because this lens is of proteins, made of proteins, and these proteins, they react with glucose, and in this reaction they are losing elasticity. This is some chemical reaction goes everywhere in our body, and the speed or rate of this reaction depends on concentration of sugar in the blood. So what can happen if you eat too much carbohydrates, like too much rice, and especially if you eat a lot of fructose and sugar, then you are losing elasticity of this lens, and you cannot see objects near field, which is close to eye. And for example, I just want to come. My wife is 21 years younger than me. Yes, but she was all her life was eating rice and mostly carbohydrates. And her eye already cannot get focused on closed objects. She cannot see what I can see very easy. For me, this near point, it's maybe 20 centimeters, 25, maybe 25. But so my eyes, despite I am much older than she is, my eye are much more elastic, and then I can get focused on closed objects. Okay, but also there is a far point of the eye, and this is the largest distance for which the lens of the relaxed eye can focus the light on the retina. Okay, and normally if your eyeball is not deformed, because it can be deformed, then you can focus on a very distant object, in principle infinity, so at a very distant object. Okay, it depends. Actually, I have little bit this. My eye is little bit deformed, and therefore I have this myopia. Okay, but we will talk about this a little bit later. So let's look how it works. We have object which can be close, and this is near point. And if the lens is stressed, it is pressing on the lens. The lens is getting thicker in the middle, and then beam is getting focused on the retina. And if it is focused, it is everything sharp, everything work good. But if it cannot be focused on the retina, then we are talking about nearsighted people. And far-sighted people are then when the the image gets focused before the retina. So okay, let's two situations. Okay, let's go in more details. Far-sightedness. Far-sightedness, it is mostly for older people. Then this lens cannot get smaller focals, cannot get thicker in the middle, so the focal length is not getting very small, and therefore the sharp image of the object is further than position of the retina, further. This has medical name hyperopia. Okay, hyperopia. How to correct it? It is people correcting with convergent lens, or so-called lens or goggles, or for reading. This positive lens, it is focusing a lens and make it closer to retina, to the position of retina. It is again older people develop mostly this type of they need this type of correction. And nearsighted people again, that it is shown that they have the object is focused before retina, so they can see near objects much sharper than objects in infinity. So what can happen sometimes, it is because the eyeball is little bit deformed and little bit elongated, so that it's little bit longer in this direction. Then it is nearsightedness or myopia. Yeah, actual myopia. Okay, then how to correct myopia? You put divergent lens before the eye, and divergent lens will make object like closer. will make object like I mean the position, the image of the created by this divergent lens will be closer to the eye, and then the image of a final image and retina will be further. So this is how this nearsightedness can be corrected, myopia. A part of these simple problems, like there are more difficult stuff, like presbyopia and astigmatism. Okay, then astigmatism is a little bit easier to understand. It is when you have not, let me look, not have, sorry, no have picture. When light from a point source is not focused to the point, but producing a line. So it is your lens in the eye works as, in part, as cylindrical, not spherical, but cylindrical lens. So the focal length in two axes, in two perpendicular axes, is different. It is not symmetric, not perfectly symmetric. And then it can be corrected with the lenses having different curvature in two axes, in two perpendicular directions. And okay, presbyopia, it is again, it is for all the people. It can be corrected with convergent lenses, which is normally people call the goggles for reading, for glasses for reading. What else we have to remember? That we can talk about the power of lens. Power of lens is measured in diopters. Diopters is equal to 1 divided focal length in meters. So if lens has focal length 1 meter, then it is 1 diopter, okay? And then for nearsighted people, we have focal length. Nearsighted people have focal length for correction negative, and farsighted people have correction length positive and positive in diopters. Okay, we can talk about simple magnifying lens. As you know, this is a convergent lens. Size of the image which is formed at retina depends on angle. This is of the object. So let's see how it works. So we have this object. Yes, we put convergent lens here, and so that the object is between focal point and the position of the lens. In this case, virtual image is created. Virtual image is created, which is not inverted. It is real. Oh, pardon. It is a virtual. It is it is not inverted. And size of this image can be much larger than size of the object. And if for proper focusing we adjust the position of the lens lens to the object, so that object looks like it is at the distance about 25 centimeters from our eye. Okay? This is the distance of the best vision, near point, so-called near point. Near point is 25 centimeters, about. For some people it is shorter, some people a little bit longer. Okay, then we are using convergent lens, and as I said, position of the object should be between focal point of the lens and the lens itself. We can talk about angular magnification of the lens, which is here. It is the angle here, theta, and here angle other. So and okay, and visible angle. Okay, so it is again angle with lens, angle without lens. So angular magnification is a maximum when the image formed by the lenses is at the near point of the eye. So the maximum magnification is 25 centimeters divided focal length of the this magnifier plus 1. Okay, let's with the single lens, it is possible to achieve angular magnification up to 4 without serious chromatic aberrations. Chromatic, because every lens, because of dispersion, because refraction index depends on wavelength, it can have chromatic aberration. So the image will have like colors, yeah. So this why if you work with simple magnifying lens, the magnification is limited to about 4. But if it is more complicated lens, it is compacted with multiple lenses, and these multiple lenses, they are made from different kind of glass with different dispersion. It can be compensated so that this magnifying lens can give magnification up to 20 with no these chromatic aberrations. Okay, let's talk about compound microscope. Compound microscope is the simplest with what we can see. It is just 2 lenses. It is in practical application. It is not 2 lenses because both lenses are actually combined from many lenses to reduce chromatic aberration. So and we can distinguish objective lens and eyepiece. Objective lens has for microscope has very short focal length, normally less than 1 centimeter, even sometimes few millimeters, the maximum. And the ocular lens or eyepiece has a focal length about few centimeters. So you see how light is going. If we have object here, then the beam which is parallel to the optical axis go here, and then it is crossing axis at focal point, then it goes again here, and then we have the beam, and we can see a virtual image which is reversed, which is a virtual image which is magnified, and it is also inverted, so it is looking other direction. Some microscopes, they are more complicated. They include some mirrors or prism, and to get this image not inverted but right, upright orientation. Okay, so let's consider again a compound microscope. If the lenses are separated by length L, and L is much longer than focal length of the objective lens and focal length of the eyepiece, then we can calculate what is the magnification of this microscope. Then the magnification of the microscope can be calculated as length, the L distance between them, between these 2 lenses, divided to F objective, this FO, this FO. Okay, we'll go. Okay, it's normally again, and so it is magnification, and we can also talking about angular magnification. Angular magnification is calculated as 25 centimeters divided by FE. FE is here. F is focal length of the eyepiece, and this is focal length of the objective lens. Here objective lens, here eyepiece. So you see this O means objective lens, E means eyepiece. Okay, and then together we can calculate overall magnification of the microscope as product of the individual magnifications. It is L, where L is distance between the lenses, divided focal length of the objective lens, and then 25 centimeters divided focal length of the eyepiece. What else? It's with visible light. With visible light, you cannot see objects which are smaller than the wavelength of light. And for green light, wavelength is 500 nanometers or half micron. And this is the limit what you can see with light microscope. With electron microscope, especially scanning or transmitting electron microscope, you can see even atoms, even sizes about 1/10 of nanometer, 1 angstrom, only such small size. And for visible light, for light microscope, it is 5,000 times resolution lower. Okay, let's consider telescope. Telescope again, we have different kind of telescope. One kind of telescope, it is made from lenses. Here it is refracting telescope, two lenses, and we have here objective lens, and here it is eyepiece lens. And or otherwise there is more advanced telescope, which is actually more expensive and more complicated little bit. It is reflecting telescope. It is Newtonian reflecting microscope, means it is a combination of eyepiece lens with a spherical mirror. Yeah. So let's consider first refracting telescope. So it has two lenses, again objective lens and eyepiece lens, and normally the eyepiece lens is shorter focal length, and objective lens is large focal length. So we are getting, with this telescope, we are getting image, virtual image of the object, which is object in this case in infinity. We are getting virtual size of the object and virtual object, and it is reversed, inverted, and it is you can say magnified, because but you can talk about angular magnification. Angular magnification depends on the focal length of the objective and lens and eyepiece lens. So it is AM magnification is focal length of the objective lens divided focal length of the eyepiece. And with this magnification is important only for observing objects which are not so far. Maximum we can see surface of the moon if it is good telescope. Maybe we can see satellites of Jupiter, and we can see Saturn, rings of the Saturn with a telescope. but distant stars cannot be resolved with such kind of telescope. They anyway just appear as small points of light. The objective lens in telescope have large diameter. Why they have large diameter? Because to get more light, the larger the diameter size of the telescope, of the objective lens, or it is or if it is a refracting mirror, the more light we can collect, and then the brighter will be the image, and then we can produce photo of the image, photo with this image, or we can see the object with naked eye through the telescope. But problem that large size lenses and mirrors are expensive and very difficult to manufacture. And weight of these large lenses, it is leading to some aberrations, so deformation of the lens itself. Yeah, and therefore people decided, okay, maybe we can make combination of the mirror together with eyepiece, and this would be cheaper and larger diameter, and they use very large diameter reflecting mirror. And mirror sometimes parabolic to reduce aberration, and because otherwise there will be spherical aberrations. And then light is not coming through the glass, it is going through the eyepiece. Eyepiece, it is small lenses, and then can relatively easy in small piece, it is relatively easy to get to reduce chromatic aberrations. Here the reflecting telescope is presented. We see parabolic mirror here. We see this small mirror, plane mirror, and we have eyepiece. Reflecting telescope, largest in the world, is located in Hawaii, in mountains, and it has size 10 meters of the reflecting mirror. But of the reflecting mirror, but refracting telescope with lenses, the largest only 1 meter diameter, because otherwise the lenses will be deformed by weight. They will be too heavy, and they are in Wisconsin. In Wisconsin, it is not very high resolution, not a lot of light that they connect. Much more interesting to use telescope in space, because atmosphere of our planet is not always transparent. It has some dust particles, it has some oscillations of the density, so it is not stable. Image is not stable, it is moving because of these variations in the density of the atmosphere. But in space it works much better, and famous Hubble telescope is 2.4 meters in diameter, and it can work in near ultraviolet, visible, and near infrared spectrum. So this type of telescope actually gives better resolution than 10-meter telescope in Hawaii, even better. So the pictures are presented here. And also this kind of spherical mirrors or parabolic mirrors are used to collect radio waves, and both on our planet, both on our Earth, but also in space. And in space we can detect some radio waves which are absorbed by our Earth's atmosphere. Okay, let's talk about resolution. It is ability of optical system to distinguish between closely spaced objects. And because if we use wave, we use light, because of wave nature of light, we are limited in resolution. So the two sources of light, if the two sources of light are close together, and what is important, they should be not coherent sources, because if they're coherent, then everything gets much more complicated. And because of diffraction, individual images consist of bright central regions and some dark rings. Okay, and here it is quite visible, so we can see two images separated. Okay, here they don't overlap, but in some cases when objects are too close, then we cannot see for sure separation of these two objects. The limit which can be used, which we can the limit of the angle, minimum angle that we can distinguish position of two objects is lambda divided A, and A is the size of the apertura, or if it is width of the slit. But okay, for telescope it is apertura size. The larger the apertura of the reflecting parabolic mirror, or if it is a lens, the better the resolution. Okay, here again we see these examples how images can be distinguished, resolved. This case is not completely resolved, and so not completely resolved, but we can yet see that these two objects. And when the images overlap, we have not resolved image. Okay, with as I said, with instead of size of the slit, we can use diameter of the apertura of the lens, and we have in this case minimum resolution angle is calculated again lambda divided apertura, and little bit maybe with 1.22. Theoretically we can use such ratio to write the minimum angle resolution. Diffraction gratings. I was in my previous presentation. You can check a link on my presentation about optical phenomena. I was talking about diffraction gratings. Diffraction gratings are used to measure spectrum of the bodies, and this is very important in chemistry, very important also in astronomy. And resolution, spectral resolution of the diffraction gratings is, this is defined as a lambda divided difference of lambda. So it is, if it has, it can resolute small differences in wavelengths. Okay, and so the larger the size of the gratings, the better is the resolution, spectral resolution. Okay, then diffraction gratings, they have different, they have diffractions not only of the first order, but high orders of diffraction, and n can be larger, and so it can be not 1, but can be up to 10, and so this is so we can talk about spectral resolution of the diffraction gratings, if it is special shape, specially produced, so that it has maximum of scattering not in the first diffraction point, but to other orders. What else also, what instrument is important? It is Michelson interferometer. Michelson interferometer was used, for example, to measure velocity of light, and also it can be used to measure differences in length or displacement of mirrors here and then. And yeah, so if one mirror is displaced, if it is moving, then we have signal which depends on position of the mirror. And even people were using such large interferometer, and they said they measured a signal from colliding dark holes. This is actually quite, I mean, I cannot believe, because accuracy of these measurements was not good enough to get the signal. They more made it some digitally, and I cannot believe that that it can be done, because the displacement in case of these gravitational waves should be so small that any noise will disturb it. So it actually was not accurate measurements. But nevertheless, for measurements of some small objects, and also for measurements of the displacement of mirrors, it is possible to use a Michelson interferometer. Here you see that one mirror can move, and then the signal will depend on this changing of the position. Okay, and so when one mirror is moved to the distance lambda divided 4, then we have change from light interference and to destructive interference. We have, instead of higher intensity, we have zero intensity, and this is called fringe shift. Okay, we can talk a little bit about electron microscope, even if it is not related to optics. We need some information about how electron microscope works. First, we have to understand that there are two types of electron microscope. Okay, first, again, what is the difference? If we use light, then we will get a colored image. Sometimes we use some special dyes to produce a more contrast image. In the electron microscope, there is of course no color, and electron microscope can work on transmission and on reflection. It's not so easy to prepare the sample to be investigated in the electron microscope, because the sample in case of scanning electron microscope, it has to be coated by metal, and in case of transmitting electron microscope, it is not necessary. So it is, but it gives not so detailed image. So okay, we see scanning electron microscope in comparison with transmitting electron microscope. So image which we can produce with scanning electron microscope can be in very good details and very like three-dimensional image, very informative. But the transmission electron microscope is working different. Electrons passing through the object, and then some denser part of samples, then not very easy to improve contrast in magnification, also limited to about 500,000. Scanning microscope is working better. It is magnification can be about 100,000 or even 500,000, but they are creating pictures of high quality which these pictures look like three-dimensional pictures. So comparison of light microscope with electron microscope, they show that the best resolution of the electron microscope is 2 angstrom or 0.2 nanometer. In the light microscope, minimum what we can use with ultraviolet light, it is 200 nanometers. So it is 1,000 times better resolution with electron microscope we can get. And but in electron microscope, the people use heavy metals and to coat the object, and in light microscope they use dyes to get colored image and to more contrast image. And of course in light microscope we can investigate both living and dead samples, and in electron microscope only dead samples which are coated by metal, or if it is transmitting electron microscope it can be without metal coating, but nevertheless it is limited in contrast. So advantages: very high magnification. Disadvantage: samples are not easy to prepare. They have to be placed in vacuum. All this electron microscope is very expensive device, and it has to operate such expensive and complicated machine, you need highly skilled operators. Okay, so okay, I'm finishing, and then the presentation. You will watch the video. Okay, thank you. Okay, guys.